Okay, so this next lecture video is on huckel theory. And this is a theory that is applied to delocalized or pi conjugated states of various molecules where you have alternating single and double bonds. And it's applying to the double bond part. It's applying to the say the pz orbitals that are sticking outside the plane of the sp2 planar pi conjugated molecule. Um, it can be extended to other systems, and I will perhaps talk about that later, or if not in the follow-up video. This provides some semi-quantitative predictions of pi to pi star transitions, which can be very useful for predicting the properties of various pi conjugated systems. And it is it's also supplies really a deeper, more accurate model um, than the resonance picture that that's first developed in organic chemistry, and so it provides better predictions of chemical reactions, relative stabilities, and say pi to pi star transitions, optical transitions in these systems. So let's start by considering a pi conjugated oligomer. The 2px, 2py, and 2s orbitals combine to form the sp2 hybridization, hybrid molecular orbitals, and that forms the sort of sigma bonded backbone of the molecule. And then this molecule is planar because sp2 hybrid MOs are this sort of trigonal planar structure. And then the 2pz orbitals stick out above and below the plane of the molecule. And you can think that they might, if we sort of linearize or we look sort of side on from the molecule so that we don't have to deal with the zigzag pattern, we can see these pz orbitals sort of sticking out of the plane of the molecule. And then the question is, it looks like there should be reasonably strong interactions between these orbitals. Indeed, there seems to be evidence of double bonding in pi conjugated systems, so that indicates that there's some covalent nature, there's some electron sharing, some actual bonding, bond stabilization in these systems. And that said, we think that primarily the stabilization is occurring between nearest neighbor carbon atoms. And then there's this question of, well, if we have multiple of these states sort of lined up, can we form some sort of collective overall delocalized molecular orbital, and is that going to affect the energy of the system? And so based on these questions, we can, and also based on our previous development of perturbation theory and the secular equation, we can develop a huckel Hamiltonian where we only include the two pz orbitals. Now, the other orbitals are there, they're around. We're just ignoring them for the time being and just sort of concentrating on one aspect of the problem, sort of a divide and conquer approach. So we're only looking at these two pz orbitals that have to do with the double bonding network in the system. And the basic approach is we take a molecule like, say, this hexatriene here, and we number all of the sp2 carbons. So we've got 6 carbons, and we just number each of them 1, 2, 3, 4, 5, 6. And then we're dealing with a Hamiltonian for all of the 2pz orbitals in this system. And the Hamiltonian matrix is going to look as follows. HII, so that's along the diagonal of our huckel Hamiltonian. That's going to be given by alpha, which is this sort of site energy. And we can think of this as the energy of the 2pz orbital sitting at carbon atom I. And that's going to, of course, have some contribution to the total energy of the system, just the sort of basic energy of the 2pz orbital. That said, that's not quite as important as this beta parameter. So for nearest neighbors, we have Hij is equal to Hji is equal to beta, and that's our nearest neighbor interaction energy. So this is equal to beta only if I and j carbons, again following that labeling scheme, only if they are nearest neighbors. And Hij is 0 if for any two carbons where I and j are not nearest neighbors. One thing we need to keep in mind here, beta is defined as negative. So it has to do with it's describing essentially an energetically favorable double bonding interaction, and so it is defined as having a negative value. So let's start by looking at the simplest case, ethylene. It's got 2 carbon atoms. Then our Huckel matrix looks like this. We got alphas along the diagonal, betas in the 2 other corners. And this gives rise to a secular determinant. Basically, we subtract E along the diagonal. So we get alpha minus E, beta, beta, alpha minus E. Those are the elements. And then, of course, we want to take the determinant of this matrix and set that determinant equal to 0. And so then when we do that, we multiply that out, we get over here, we've got alpha squared minus 2 alpha E plus E squared minus beta squared. And of course, we can apply the quadratic formula. In this case, A would be the constant associated with E squared, so that would be 1. B would be minus 2 alpha, that would be the constants associated with e to the first power. And then, of course, the leftover constants would be alpha squared minus beta squared. And so then plugging that into the quadratic equation, collecting terms and simplifying, it boils down to a nice simple result. E is alpha plus or minus beta. And again, that's directly from the quadratic equation. I skipped a couple of steps, but you should be old pros at the quadratic equation, or quadratic formula by now. And I don't want to get bogged down in that. This isn't a pre-calc course. Okay, so then essentially we end up with 2 energy levels, an alpha plus beta energy level. That's our lowest energy level because beta, again, is defined as negative. And then we have this other energy level, alpha minus beta. That's a higher energy state. The energy difference between these 2 levels is going to be 2 beta. And we have 2 electrons in the double bond of this system, or in the 2pz orbitals, and you can go through and do some electron counting if you're not sure. And there should be 2 electrons. Again, there's also 2 electrons in the second bond of the double bond. That's our basic rule is 2 electrons per bond. And so putting those 2 electrons, then we've got 2 electrons in this alpha plus beta orbital. And, or we can think of that as 1 double bond in this system, giving us 2 electrons in the pi system. And so our total energy is going to be the energy of the first electron plus the energy of the second electron, or 2 alpha plus 2 beta. So that's the total energy of the pi system for this molecule according to the Huckel model. Now we can take our known energy of the individual orbitals and find the C1 or C2 linear coefficients associated with the 2pz orbitals. We start with our sort of matrix equation here, rearranged slightly, and so we're taking, instead of h psi equals e psi, we'll have h minus e along the diagonal times psi equals the 0 column vector. And so then from matrix multiplication, we get that C1 times alpha minus E, right, doing the sort of rule where the matrix multiplication rule, where you move your left finger in a horizontal direction, and you move your right finger down and follow along. You get alpha minus E times C1. plus C2 times beta equals 0. And then we get a second equation, beta C1, or C1 beta, plus alpha minus E C2 is equal to 0. So from these straightforward equations, if we plug in E equals alpha plus beta, then we get C1 alpha minus beta plus C2 beta equals 0. And of course the alphas cancel, and we get minus C1 beta plus C2 beta equals 0. That can only be true if Z1 equals C2. So this ends up being a symmetric wave function where both of the linear coefficients are positive, or they're both negative. They're both the same sign. Now we can impose a normalization scheme. Typically for huckel, we use the sum of the square of the coefficients has to be equal to 1. And so that's going to give us, and again, that's just kind of a standard method, although it's not taking into account the overlap integral like we were talking about in the case of H2 plus. So there is some overlap, but we're sort of ignoring that. And we have this simplified normalization scheme for huckel, where we just say the sum of the linear coefficients squared has to be equal to 1. And so then that gives us C1 equals C2 equals 1 over square root of 2. And our wave function for this state is going to look like this: 1 over square root of 2 times 2pz for say atom A, or first atom, plus 2pz for atom B. And again, that's just the shorthand for psi 2pz, or psi for A and B. And so if we sketch this, it's going to look like this molecular orbital here, where the 2pz orbitals on both atoms have the same sign, and so they overlap and they combine together to form this molecular orbital. And we're showing it here in a way that clearly shows that there's electron sharing occurring between those two carbon atoms. For our other state, we can plug in the other energy level equals alpha minus beta. This yields C1 equals minus C2, and so this is the state where the wave functions change sign, and the wave function can be expressed as this: 1 over square root of 2, the first wave function for atom A minus the wave function for atom B. And so this means that there's going to be a sign difference, and this is shown in our sketch here. There's this nodal plane in the middle between the two carbon atoms. You get this sort of butterfly-shaped antibonding pi star orbital. We can also, of course, look at the overall bonding in this system, overall pi bonding in this system. The number of pi bonds in our system, the number is equal to the number of electrons in pi bonding orbitals divided by 2, and so that's going to be 1. The overall carbon-carbon bond order is 2, because we also have a sigma sp2 bond between the two carbons. Now let's move on to a larger system, sort of building things up. Let's look at 1,3-butadiene, the subject of many bad chemistry puns. Help me, I'm diene, that sort of thing. Anyway, so let's number our carbons: 1, 2, 3, 4. Then that's going to lead to this kind of secular determinant where we have alpha minus e's all the way down the diagonal. We have betas for atoms 1 and 2, carbons 1 and 2, between carbons 2 and 3, and carbons 3 and 4. Notice that, even though our stick structure doesn't show a double bond between atoms 2 and 3, we're still going to include a beta there, and that's the rule. If it's sp2 and if it's an sp2 carbon and they're nearest neighbors, then they get a beta. and we plug things into the matrix, and then at the end, when we look at all the molecular orbitals, we can decide where the double bonds sort of belong. So our model is we're not supposed to sort of force the model to a certain conclusion. We put in all of our sp2 carbons and then let the bonds end up where they may. Now, unfortunately, this is not one where we can easily, we can't apply the quadratic equation. There probably are some tricks we could use, but it's probably not worth all the effort. We can plug all this into a computer, and I have a separate set of notes that describes how to do that. And we get alpha plus 1.62 beta as one of the energy levels. That's the lowest energy level. Another one, alpha plus 0.62 beta, alpha minus 0.62 beta, and alpha minus 1.62 beta. And so we end up with this not quite evenly spaced, although I sketched here evenly spaced, ladder of energy levels. Right, the energy difference between the lowest two levels is 1 beta. The energy difference between 2 and 3 is about 1.2 beta. So they're almost evenly spaced. We've got 2 double bonds in this system, so we have 4 pi electrons, and so this is how the energy level filling diagram looks, and so I put the up-down arrows there to show the filling of the pi electrons, and then over here at the right I've sketched orbitals, and again we haven't gone through, but a computer can spit out what the various linear coefficients are, and then based on those linear coefficients we can sketch these orbitals. There's this lowest energy state where essentially all of the the linear coefficients are a little bit different for each carbon, but they are all positive, and so it combines to form this kind of this totally symmetric or most symmetric orbital, where we just sort of have all of the orbitals with the same sign, and they're all combined together to make this big, massive, highly delocalized molecular orbital. And of course, it has a relatively low energy, right? Alpha plus 1.6. Then the next one has a single node in the middle of the molecule, a little bit higher energy. So there's kind of antibonding character between those central two atoms for this particular orbital. And of course, this leads to a little bit of a difference in the bond order between carbons 1 and carbon 2 and carbon 2 and carbon 3. So this is actually showing some overall difference in the pi bondings between the various carbons. But again, we haven't forced the issue. It just sort of falls right out of the calculation as a prediction, right? So we don't want to force our prediction, and we haven't. Yeah, it has a node in between those central two carbon atoms, and it looks like this. Then the next one has 2 nodes. That one's not occupied, so it's not so important. It's not really going to affect the structure of the atom. And then, of course, the highest energy state has 3 nodes, and essentially alternating signs between each of the orbitals. And this is a theme that we see repeating over and over again in these systems. Sort of the lowest energy state has no nodes, except for the nodes that are sort of baked into the 2pz orbitals that are part of their nature, but there's no additional nodes. Then the next higher state has 1 node, above that 2 nodes, 3 nodes, and so on. And this is a fairly general rule, and it also agrees well with what we've seen in other quantum systems, the particle in a box, the harmonic oscillator, and so on. Now let's consider whether or not there is stabilization, or some kind of pi conjugation stabilization in this molecule. We can calculate the total energy by adding up the energies of each of the 4 electrons. That's going to give us, we've got 2 electrons in the alpha plus 1.62 beta, and we have 2 electrons in the alpha plus 0.62 beta. Adding all that together, we get 4 alpha plus 4.46 beta. Now, if we compare this to just two ethylene molecules kind of side by side, but not linked, right, in this pi network, we would get 4 alpha plus 4 beta. So our butadiene has a lower overall energy than ethylene. So this pi system of butadiene is more stable than the analogous pair of ethylene molecules and its associated pi system. So it really seems like there is a pi conjugation or a delocalization stabilization in this system. And we can think of this as maybe being due to a reduced confinement energy. The electrons can spread out, and we know from the particle in a box, this gives a lower energy. We can also notice that, I made mention above that the wave functions look a little bit like particle in a box wave functions. There's a resemblance. They don't look exactly, but we can see some similarities. Now if we move on to benzene, not only does that have more atoms and a bigger matrix, and it's a little bit lopsided here, we have these alpha minus e's all along the diagonal. We have the betas in the just right off the diagonal terms there, indicating the various neighbors, 1 and 2, and 2 and 3, and 3 and 4, and 4 and 5, and 5 and 6. All of those would give rise to beta terms there. And then there's this additional beta in the corners related to the atoms 1 and 6. So this is one of the differences in the secular determinant for the cyclic molecules as compared to similar linear molecules like the just sort of linear hexatriene. So the Hamiltonian looks different. It turns out this actually, you can make some guesses. You can plug in just a wave function with all ones on each of the 2pz carbons, and you get this totally symmetric orbital, and that has an energy of alpha plus 2 beta. Then there are two more states, alpha plus beta, those are degenerate. Then there's alpha minus beta, those are also degenerate. And then there's an alpha minus 2 beta. And so you get this MO diagram, which strangely looks a little bit like a benzene molecule, where we've got an energy level at the bottom, an energy level at the top, and then these two pairs of degenerate energy levels in the middle. If we see, we have 3 double bonds in the system, so that means that we have 6 electrons in our pi system. And so if we fill that up and then count up all of the energies of each of those electrons, our total energy is going to be 6 alpha plus 8 beta. And so this is actually ends up being 2 beta more stable than 3 ethylenes. If we had 3 ethylenes, we'd have 6 alpha plus 6 beta. But here we have 6 alpha plus 8 beta. So there's this additional stability because we have a, perhaps because we have a cyclic system. In fact, we can also compare to, and this observation of this additional stabilization for benzene is what led to this and Huckel's development of this model, led to Huckel's 4n plus 2 rule for aromatic molecules, that there's an additional stability for these kinds of molecules. Benzene is also more stable than, it's not just the fact that we have 3 double bonds, also the fact that it's cyclic that's important, because if we calculate for linear hexatriene, I'm leaving out the result, or I'm leaving out the intermediate steps in the calculation, but the final result is E equals 6 alpha plus 7 beta, or a little under 7 beta. That's what my computer was telling me. So that's less than, or sorry, that's higher in energy than the total energy of the benzene, right, which has 6 alpha plus 8 beta. So it's more stable than linear hexatriene, and so again, this supports this notion of this Huckel's 4n plus 2 rule. Now let's consider the UV vis spectrum. We plug our electrons into this system, and we see that our HOMO to LUMO transition for the system is going to have an energy of 2 beta. And we can actually determine beta from, looking at some range of aromatic systems, and then finding this empirical beta parameter by sort of fitting. And then we can apply it to a range of other aromatic systems. We can look at the whole sort of acene series, going up from benzene to naphthalene, anthracene, tetracene, and so on. And this ends up giving you a reduced gap as you go further and further down the acene series, down to where tetracene actually has a nice absorption in the blue, which leads to an orange, or in the blue-green, which leads to an orange color. Pentacene has more of a red color. A couple final notes on this huckel model. Of course, we're going to use it to look at extended states in solids, but Roald-Hoffmann extended huckel, actually including terms for various sigma bonds, and this is the so-called extended huckel model, and that formed the basis, or he used that to make a lot of predictions about reactivity and reaction results for a range of chemical reactions involving cyclic or nearly cyclic species, or cyclization reactions, things like that. Reactions where some of the intermediates might be cyclic, or the final, either the intermediates or the reagents or the reactants might be cyclic. So he used the extended huckel results to develop his Woodward-Hoffmann rules, and he won the Nobel in 1984 for that. And another similar method yields essentially identical predictions, and that's the frontier molecular orbital method. But I'm not sure, but perhaps the frontier molecular orbital method is not as well grounded, at least in such a simple, elegant theory. All right, so that's all I have to say about huckel model for now. We can apply it to a lot of different systems. We've really only scratched the surface here. And again, we're also going to apply variants of this to various to metals and insulators and that sort of thing. And the Slater-Koster type binding theory is closely related to this huckel model. Okay, and that's the end of this lecture.